Okay, so welcome again to the course Fundamentals of Solar Photovoltaics and Technologies. So in this new lecture, we will again continue with our discussion on basics of semiconductors. So just to briefly recap, what we did in the last class was to look at the semiconducting materials and that they have an energy gap between what is called as conduction and valence bands. And the relative position of maxima of valence band with respect to the minima of conduction band in the energy wave vector diagram, that is EK diagram, determines whether the material are direct band gap semiconductors or indirect band gap semiconductors. So you can see on the left, for a direct band gap semiconductor, the minima of conduction band and valence bands maxima, they coincide at the same K value. So materials like gallium arsenide, they are direct band gap semiconductors and they tend to have better light absorption and light emission characteristics as compared to indirect band gap semiconductor, which are shown on the right, where conduction band minima does not coincide with the valence band maxima. As a result, there is a necessity for phonon assisted transition in the optoelectronic processes, which is inefficient process as compared to that in the direct band gap semiconductors, and silicon is one prime example of this kind of materials. And also we also looked at the relative difference between the metals and semiconductors with respect to band structure. So metals exhibit partially filled valence bands or overlapping conduction and valence bands, as we can see here on the left. Metals like sodium, which have only one unpaired electron, they have partially filled valence bands and then remaining states are empty within the same band. As a result, these states are empty for conduction to occur. In case of magnesium, which have two electrons in the outer shell, the valence band is filled, but then there is a conduction band which is empty but overlapping with the valence band. As a result, the electron in these states can seamlessly transition to the empty states in the conduction bands, leading to conductivity in these materials like magnesium. And also we looked at the insulators and semiconductors. Insulators are materials which are band gap more than 2.5 electron volt, approximately speaking, and they have the gap, this gap is pretty large, so electrons will not be able to overcome the filled valence band states to go into a conduction band states without supplying a large amount of energy, and as a result these materials are called as insulators. So it's very difficult for electrons from the valence band to access the vacant states in the conduction band. Semiconductors, on the other hand, they have moderate gap, less than 2.5 electron volts on a general note, and here if one can apply sufficient magnitude of light stress or thermal stress or electrical stress, the gap is narrower. As a result, electrons from the filled valence states can occupy the conduction band states, leading to conduction. So prime example of insulator would be something like diamond or even polymers, many ceramic materials which have high band gap. Diamond has 5.4 electron volt, which is indeed very high, but many other ceramics also have very large band gap. Silicon, on the other hand, which is a semiconductor, has a band gap which is moderate, 1.1 electron volt, and most of the semiconductors that we look at for photovoltaic applications, they tend to show a gap of approximately 1 to 1.5 electron volt, a few points here and there. So if you look at semiconductors, semiconductors can be classified in different categories. We can have elemental semiconductors such as silicon germanium, which are basically group 4 semiconductors. Then we have 4,4 compounds such as silicon carbide, which could be a ceramic. Then we have 3,5 compounds, so group 3 and group 5 elements coming together, giving rise to more ionic character in the materials. So materials like aluminum phosphide, aluminum arsenide, aluminum antimonide, gallium based compounds and indium based compounds coming together to form different compounds. Obviously, as you go down the column or as you mix different elements, the melting point and band gaps change. If you look at the 2,6 compound, they mix group 2 and group 6 elements. So zinc based compounds or cadmium based compounds are prime examples of 2,6 compounds. Then we have 4,6 compounds such as lead sulfide, lead selenide, lead telluride, and then alloys such as silicon germanium alloys, aluminum gallium arsenic alloys, aluminum gallium nitride alloy, where one can vary the proportion of two elements like silicon germanium and silicon germanium alloys, aluminum gallium in gallium arsenide. So, you can dope it with aluminum, or you can go dope gallium nitride with aluminum. So, if you wanted to know more about these, I recommend you to going to this book, Advanced Semiconductor Fundamentals by Robert Pierre. So, the intrinsic silicon at 0 Kelvin, we know that valence band is full, the conduction band is empty, and there are no bonds which are broken. As a result, there is no electron density in the conduction states. When you apply the thermal stress or photo excitation, then we basically break these bonds, and as a result these electrons and positive charges that we create. So, basically what it means is that bonds are broken, which means you are able to excite these electrons from valence states to the conduction states, and once the electron is moved into conduction state, it leaves empty states on the back behind in the valence band, and this is called as a hole, which is a positively charged particle. And at room temperature, this material will consist of approximately, since for every electron you create one hole. So, let us say if electron density is n, which is equal to one hole, this is called as intrinsic carrier density, and this is approximately equal to 10 to the power 10 per centimeter cube. So, now we will see how do we determine this carrier density in the semiconductors from very basic principles. So, first thing about the materials is that we look at the Maxwell distribution. We see that average energy of electrons at room temperature is about kT, which is 25 milli electron volt, and typical band gap of a semiconductor is about 1 to 2 electron volt. So, the question is, how are then electron excited to conduction band at room temperature? Maxwell distribution suggests that you can see this is probability of occupation as a function of energy. So, you can see that even at 100 Kelvin, it gives you a large probability of occupation around half electron volt, and if you increase the temperature to 200 to 400 Kelvin, this gives you even larger distribution, even larger density of carriers, and the probability of electrons going into conduction band is very large. This was modified to some extent, what we call as by Fermi-Dirac process, as we will see in the next few slides. But before that, let us say we have certain electron density which is able to conduct at higher temperatures. So, let us say when we have a semiconductor, we can define the bands like this, and when you apply a potential to a semiconductor, then the bands bend. So, you apply electric field in this direction as shown by the arrow, and consequently you will develop a potential, and the bands will bend in the opposite direction because the energy will be nothing but minus of QV. So, basically the potential energy can be written as minus of EVx, and since both electron and hole lead to conduction, the current density can be written as J is equal to sum of electronic current plus hole current. And assuming that they have, and the fact that they have similar charge, we can write this as, so this is electronic current and this is hole current, and this is the total current that you will obtain from a semiconductor. And to calculate what we call as conductivity, we need N and P. So, basically J is nothing but sigma E. Sigma is what is called as conductivity, and conductivity you can see is given as Ne mu. So, for calculating the conductivity of a semiconductor, you require N. So, what is this value of N? Is it the one which is predicted by Maxwell distribution, or is there a different distribution that takes care of it? So, we need both N and P for calculating the conductivities. Here we can define drift velocity of electron as mu into E, which is the product of mobility and electric field, and mobility is defined as mu, which is equal to E tau divided by m star. E is the tau is the relaxation time, and m is the effective mass of the carrier. So, obviously when you apply potential, you can see that electrons will go down the conduction band and holes will go up the valence band. That is how the conduction takes place. So, electron prefer to go down the energy and hole prefer to go up the energy. It is like a balloon going up in the air. So, this distribution of electron is explained by what we call as Fermi-Dirac function. Fermi-Dirac function it modifies the Maxwell distribution by the equation Fe, which is the probability of occupation of an electron at an energy E, is equal to 1 over 1 plus exponential of E minus Ef divided by kT. So, if you plot this equation as a function of, so this is your energy, this is your Fe. So, at 0 Kelvin what we will obtain is something like this. So, this is what we should get at 0 Kelvin, because probability will vary from 0 to 1, and this is the energy Ef. So, which means probability of occupation of energy levels below Ef is equal to 1, and this is at temperature T is equal to 0 Kelvin, and it is 0 at energy levels above 0. Now, this equation what it tells you is that as you increase the temperature, the curve changes its position across something like that. So, basically what it tells you is that this is half. So, basically it tells you that the electron, these are the, so in this region what has happened is the probability of occupation has decreased, and the regions above Ef the probability of occupation has gone up. So, basically what it tells you is that this is the region from which the region on the left is the one where electrons have left, and region on the right where electrons have occupied. So, basically the ones depending upon the magnitude of energy, the states near Ef, that is E less than Ef, become empty because electrons have gone here. So, these are the states which are the now filled states. These are filled states by electrons jumping from E less than Ef. So, these are states at E greater than Ef. Okay. So, what it tells you is that it is not all the electrons which take part in conduction. It tells you that it is only those electrons which are in the vicinity of Ef, they take part in conduction. So, it is electrons within this band, they will take part in conduction. So, this is a narrow band. Of course, for the sake of illustration I have exaggerated it, but otherwise it will be even narrower. So, as a function of temperature, if you plot it at another temperature, this would be something like that. So, this temperature would be T1. So, T1 is greater than 0 K. This temperature would be, the red one would be T2, which is greater than T1. So, as you keep on increasing the temperature, more and more states below Ef, the electrons start hopping from those states to the higher states. Now, this is what is called as Fermi-Dirac distribution. So, basically it tells you the probability distribution of energies for a large ensemble of electrons as a function of temperature. So, basically we know that number of electrons in a crystal. Earlier analysis that we saw that most of the electrons, most of the models considered only one electron, but solid has many electrons. It can consist of about 22 or within that ballpark figure number of electrons. So, basically that is a very large number. Per centimeter cube you can have about 22 electrons. So, as a result there is a need to determine the distribution, number density of electrons in a crystal. So, for this we first need to determine what is density of states. This means how many energy levels are contained in a given interval delta E at a given energy E in what we call as K space, or it is called as phase space. So, if you draw this figure is between different values of K. Let us say this is Kx, this is Kz, and somewhere here you will have Ky. So, these are all three orthogonal K spaces. So, it is between, so this is like a sphere, okay, a sphere of volume. So, corresponding to basically what we are saying that corresponding to EF there is a wave vector called as KF, which is called as Fermi vector. So, this defines the upper limit of Fermi sphere. So, basically you will have a sphere like this and whose radius is KF, and all the K points that we are considering will be inside this sphere, and states are quantized. So, we cannot have continuous states, we have to have discrete states. So, if you look at this, this is like a sphere, something like that, and within this sphere we can have these quantum states like 1 state, 2 states, 3 states, 4 states, and each of them are separated by a value called as k. So, in x direction, in z direction, and in y direction. So, they are separated from each other. So, basically you can say the upper limit is a sphere of radius kf at 0 Kelvin, which means all the states are within that sphere are filled, and since there are so many states, there are 22 electrons, you can say there are infinite number of states, which means you can approximately consider this as a sphere. So, this is a sphere of radius kf that defines what we call as Fermi sphere, whose maximum limit is EF, and there is a correspondence between KF and EF, and this sphere consists of k states, individual k states or discrete k states separated by 2 pi by L length, which is nothing but k vector, right. This is the magnitude that you will have. So, if you have electron in a box called as L dimension L, then your in the reciprocal space the smallest unit will be 2 pi divided by L. So, each of these will be separated by 2 pi divided by L. So, this is how it will look like in. So, basically if I represent this in 2D, distribution of energy levels in a band, then Kx can be written as 2 pi Nx divided by L, Ky will be 2 pi Ny divided by L, and Kz will be equal to 2 pi Nz divided by L, and N, Nx, Ny, Nz are integers, and they can take the value 0, 1, 2, 3 and so on and so forth. Okay. And if I just draw on 2D for 2 dimensional K space, then each of these will be separated by a distance 2 pi divided by L, and this is how it is going to look like. And energy as we saw electron in a box model, that E is nothing but it was n square pi square h cross square divided by 2 ml square, and h cross is equal to h divided by 2 pi. So, I can write this as n square h square divided by 8 ml square. I can also write this as E is equal to h cross square 2m into kx square plus ky square plus kz square in the 3D. So, we can say that total number of orbitals which are present inside a material is nothing but the radius of a sphere, which is 4 by 3 kf cube, divided by the volume of each state, which is 2 pi divided by L cube. And if I multiply it by 2, because the electron has 2 spin, one spin up, spin down, if I consider the factor of spin, then total number of possible orbitals are n is equal to 2 into volume of Fermi sphere divided by the volume of individual k state. Okay. So, this is volume of Fermi sphere, and this is volume of individual k state. Okay. This gives me total number of states below Fermi level at 0 Kelvin. Okay. So, density of states is basically the number of energy states per unit energy in the energy interval dE. that is the which is called as density of energy states. So, I can write I can define density of states being equal to dN divided by dE. If I then differentiate this, I can write K is nothing but E is equal to h cross square K square divided by 2m. So, if I take that as a equation, I can differentiate this equation and get through an analysis dE is equal to V divided by 2 pi square into 2m divided by h cross square to the power 3 by 2 into e to the power 3 by 2. This will depend upon whether we do this analysis for 1D, 2D or 3D. Okay. So, in 3D we get a relation e to the power half, in 2D we will get a relation e to the power 0, and for 1D we will get a relation e to the power minus half. Okay. So, this is through analysis which you can see in any solid state physics book. So, if you wanted to go through a detailed analysis, you can go through Electronic Properties of Materials by R.E. Hummel or Solid State Physics by Charles Kittel, and that is a straightforward analysis. So, the carrier concentrations then I can define as number of electrons per unit volume in the conduction band is nothing but. So, now what is number of electron? Number of carrier is equal to product of, basically I can say, density of states. Density of states will give you the number of energy states multiplied by probability of occupation. So, obviously, if you do this at 0 Kelvin, then this will be 0, because in conduction band there is no electron. The probability of occupation at a temperature, so at T is equal to 0 Kelvin, Fe is equal to 0 for E greater than Ef. So, all the conducting states are empty, which means there is no carrier density there. But at T not equal to 0 Kelvin, that is at T greater than 0 Kelvin, F for E greater than EF, greater than or equal to EF is not equal to 0, which means there is a finite probability for electron to occupy the states higher states, which means I can write number of carriers is equal to product of Fe into dE integrated over all the energies from EC to infinity. Similarly, for holes I can write P is equal to minus infinity to EV. So, we can see that these are the states. This is your, now going by the relation, this is e to the power half relation. So, this is your conduction states, this is your valence states, this is your energy level, okay, and this is your energy gap. All right. So, these will be empty at 0 Kelvin and filled at 0 Kelvin, but the moment you start increasing temperature, something from here will get excited to here, creating a hole here and electron there, okay. And this is a product of your density of states multiplied by the probability. So, whole probability, as we said earlier, is 1 minus Fe into dE into integrated over minus infinity to EV. So, Fe is fraction of states occupied at a temperature T, and dE is density of states per unit volume per with energy element dE. We can apply a Boltzmann approximation there when EF is well within EG. So, EF for semiconductors will lie right within the semiconductor. So, EF is well within EG, and we can say that EC minus EF, so this is your EC, this is your EV. So, the distance between the valence and conduction band edge and the Fermi level is more than 3 kT, okay. That is the approximation that we make. So, this is basically Boltzmann constant. So, we can write this approximately as Fe can be written approximately as exponential of minus E minus EF divided by kT. So, basically this equation, these two equations give me number of electrons per unit volume in conduction band, and the following equation gives me number of holes per unit volume in valence band. probability of occupying an energy level is given by Fermi-Dirac statistics, and that is how we simplify this whole thing. So, if I now plot here I am plotting dE. dE will be very large. So, let us say 0 and this is 10 to the power 26, somewhere in between, let us say this is 1 into 10 to the power 26, this is 3, 2 into 10 to the power 26 per centimeter cube EV. Okay. And this is on the y axis, we can write this is energy in EV. Okay. So, Fermi level we take that as a reference energy. So, let's say this is my 0 energy, this is your Fermi energy in between EF, somewhere here I have. So, if you look at Fermi-Dirac function across the EF will go as something like this, something like this. Okay. This is your Fermi-Dirac function, this is your Fe. Okay. So, on the y axis of course, it will be Fe, and if I want to plot now density of states for conduction band and valence band, let us say they are equally. So, this is your EV, this is your EC, and let us say this goes in this fashion and this goes in opposite fashion in this direction. This is your DC. If you look at now this plot, what I can do is that this little lobe here, which is product of Fe and dE, and similarly a little lobe here, because 1 minus Fe will be here. So, this little lobe here, this will give me what we call as Ne, and this will give me Pe. This is your electron density, and this is your hole density. So, of course, this is at a temperature 0 Kelvin, and as you increase the temperature, so of course, on y axis you can plot Pe, Fe from 0 to 1. So, this will be 0, this will be 1. So, basically what it tells you is that, and this will be half along this axis. So, basically what this tells you is that at a finite temperature, it is the spread of Fermi-Dirac function which gives you finite carrier density in both conduction and valence bands, even for a pure semiconductor. So, even if the band gap is, let us say, about 1 electron volt, you will get finite carrier density because of a spread of Fermi function across the EF value in both conduction and valence bands, and the product of density of states and Fermi function or probability of occupation for both electron and hole will give you electron and hole densities. So, what we have done is we have seen that how do you calculate the electron and hole densities in intrinsic semiconductors. This is a very important point because now we are able to calculate the carrier density. So, now if you are able to calculate the carrier density, sigma is equal to Ne mu E plus Np or Nh E mu H. We can calculate both and Nh, sorry, this will be Nh, yeah. You can calculate both Ne and Nh. This is your electron density, this is your hole density, and we can calculate the total conductivity for this semiconductor is called as intrinsic semiconductor. Intrinsic meaning pure, this is called an intrinsic, and here Ne is equal to Nh. Okay. So, we will take this discussion further in the next class, and also see that it is not pure semiconductor we often use in semiconductor devices. We use what we call as an extrinsic semiconductor, which is intentionally doped with certain impurities to give it a defined character. Thank you.